So we're going to today be talking about when things go bad in programs, ways in which we handle them. But for those in 371, we're going to be going a little bit lighter on some of the details about when we use each of these techniques, just hitting it quickly. And then we're going to be introducing a more scalable and robust way of handling errors that are normally indicated with exceptions or return codes in a way that's type safe, that's scalable, that's high performance, and frankly beautiful as well. So we're going to see how these things called monads can aid in that. Okay. So the idea here is that bad things happen in when programs run. Things happen that are unexpected or are rare, and we have to handle not just the typical case, not just the average case, but all cases to build software that's robust. And when we're dealing with, as we increasingly are, with large volumes of data in an increasingly interconnected world, these things tend to happen quite a bit. So we might get a divide by zero error because we have massive amounts of data and one of them just happens to be zero. It shouldn't be, it's actually due to a poor measurement, but it is, and it causes a divide by zero somewhere in our pipeline of processing. Or, there's a network disconnection and a timeout, or some website that we're using to scrape some data from it, it's down. Things happen. Things happen. There's race conditions and concurrency. There's cases where machines have faults. And one of the lessons for distributed computing in our increasingly complex computer environments is that we can't build scalable systems unless we're robust to failures, unless we're robust to problems. So bad things happen, and we as software engineers like to think about the typical case where the work gets done in most cases, but we need to also handle the problematic cases. We need to be mature. We need to be able to handle it when things go bad. And there's three primary problem handling approaches that I am going to hit on, and then I'm going to talk about this fourth one, which really combines the best features of the first two, while still leaving a big room for assertions. And in fact, we're going to see how to perform assertions at a higher level due to the sorts of language features we're talking about than I've had time to cover in 371. So I'm going to be talking about return codes and exceptions, introduce when we use each of them, and contrast that with when we use assertions, and then talk about how monadic methods, using tools like values that maybe encode a value, they're optional values, or that have a try value, and then encapsulate success or failure, how that can be used to build more robust programs. So the first thing we're going to talk about is return codes. And return codes are used and have been used for decades and decades to indicate success or failure, to indicate problems when they come up, to indicate things that that need to be handled. But the way in which we handle them is we use a value that's distinguished or unusual. So maybe we reach the end of a file in something that is reading each line, and it's got a signal on at the end of the line. Or the last item in a linked list. We use sentinel values to indicate that. Or item not found in a data structure. We look up a value, and we need a way of saying, hey, I couldn't find that item in this dictionary. And the ways in which we use these is we have some value that's distinctive. Maybe we're looking up the index of an item in an array, and if we can't find it, what might we return? -1, because it's, in most languages, -1 is not a legal index into the array. Why do I I say in most, incidentally? Yeah, Python and actually several other languages. R, for example. There's actually a -1 to indicate the last item in the array. So we try to pick a distinctive value. If it's -1, maybe it's min int, the minimum possible integer, what have you. We pick a distinguished value, and we try to return that to indicate, that something has gone wrong, that something unusual has happened. Or maybe the need is as simple as we want a function that returns did it succeed or fail, and we use 1 or 0 to indicate those. So this is lightweight. It's a simple idea. It's nothing fancy. We're just returning a distinguished value of the type that we normally do. And it's very lightweight. It has almost no performance cost. What are the disadvantages of this? What could people see as a risk or a problem? What could go wrong? Okay, so maybe you return -1 to indicate that you couldn't find this item in the vector. What could be a problem with that?
You don't check for it?
Yeah, you don't check for it. There's no checking for it. As far as the calling code is concerned, it's just getting back an integer. And it may use that integer to retrieve the value there, right? In that index in the array. And then bad things happen. Bad things happen. Or you may return a null value, right? To indicate I couldn't find this item, and that null gets dereferenced. It tries to use it to refer to a person and asks for their name, and bad things happen. So we don't check it is one of the big things. What's another problem that could come?
If multiple errors, you have to represent them in multiple different ways.
Yeah, we have to represent them in multiple different ways. Okay, suppose we have a program that has several of these sorts of situations where we return different integers to indicate different problems. What might be, so suppose we have different outcomes and we want to indicate them with an int. What could go wrong there?
There's no meaning associated.
Yeah, it's not clear. Does a 0 mean success or failure? In Unix, does 0 mean success or failure? Success. In other programs, 1 means success, 0 means failure. And it's not clear what that means. And in general, when we use return codes to encode different possible values, there's no guaranteeing the same convention is adhered to by different parties engaging in the software development. And and again, it relates to the fact that, as Janelle said, there's no privileged status to the values. There's no canonical meaning to these values. So handling is not enforced. There's risk of inconsistency, risk of misinterpretation of them. And you can have wildly odd things done, where, and this is generalizing the issue, if you're using numbers, integers to represent things, you could have a 1 and you think it means male and it actually means New Brunswick as a province, and we assign a sex to the province that a person's associated with, because they're just integers. There's no semantics, there's no meaning saying this is an integer encoded province, this other one is an integer encoded sex. And you may get misinterpretation of them as well. There's no metadata captured about what went wrong either. Okay, you return a 1 to indicate there's been a problem. Well, what sort of problem? Then you can divide it up into pieces, but even there, that might not be enough to have 1, 2, 3, 4. And I think all of us have suffered the fact of cryptic error messages or cryptic error code, right? I don't know how many of you use Windows for bizarre error codes. They tend to be in hex, and to start with 8,000. So you received error code 8000 F11B. Thanks very much. I'm a computer scientist, and it doesn't mean a lot to me. You can appreciate how much it would mean to, your average user. So, some real problems here. There's a lack of type safety. This is a lake of type safety, and I enjoy swims in the lake of type safety, but what I really mean here is lack of type safety. Okay, there's no enforced awareness. It doesn't check that you'll handle it. It doesn't check that it's being handled differently than a normal value. Now, another issue is that there can be difficulty in using higher order functions in this context. You pass in a function to another function like map or what have you, and you want to be able to handle an unusual condition separately, but from map's perspective, it's just another int. And so it doesn't handle it differently. We could add it to another value in a meaningless way. It's just encoding, this different value. It can be difficult to apply to type parameterized code. What do I mean by type parameterized code? Remember back. Remember map and append? Maybe not. We had a function. Hey, let's type some code. What do you think? So here we go. Here's Scala, right? Remember map and append? We did def map and append. And what was different about this? Does anyone remember? It was type parameterized, ladies and gentlemen. It was type parameterized. So we could take here a function from t to, and we could make it t to u if we wanted to, but I'll just do it t to t for ease here. And then we took in a sequence A, which is of type sequence t, and a sequence B of type sequence t, and we said, okay, this is equal to sequence A dot map of the function appended to sequence B dot map of this function. Okay, that's a type parameterized function, meaning we could apply this to sequences of strings or sequences of ints or sequences of doubles. And if we wanted to have a function that could indicate some weird condition, if that function is generic, it's going from some type to some type, how are we going to indicate across all different types that something strange has happened? It can't handle this case or something. Maybe we wanted that to be omitted from filtered out from the value returned. We can't really indicate that. It's type parameterized. Lack of canonical values. There's also an issue with verbosity around handling. You got to have if it's this or that, what have you. So there's some ways we can ameliorate this in traditional languages, and I'd encourage them. I don't want to demean them. It's not like languages are totally can't do anything about this. They can. So languages like Java, C++, etc., these languages we know and love, you can use enums to indicate these values. So you have a province enum, you have a sex enum, and those are different things. And behind the scenes, maybe they're encoding things under the covers as ends, but they're touch safe. You can't assign one to the other, right? You can actually get it to help you make sure you handle all cases of it, for example. Clearly delineate values, you can leverage compiler checking, and you can be sure to always explicitly handle all values. And you can define the default value as illegal. That's what we call offensive programming. We'll soon see in the latter part of today, and probably some of Monday, we're going to see how monads that maintain values with some metadata basically secure the advantages of return codes without much of the shortcoming. So we're going to come back to return codes. Return codes are great for common expected events. These are not unexpected events. The end of file, you're going to reach the end of the file very likely anyway. You're going to reach the last value in that linked list. you're going to look up a key that's not in the dictionary sometimes. So these are great, lightweight, common for handling those common events, but we'll see how to do them one better as monads. This will be kind of return codes in a type-safe, scalable, general purpose way that will handle type parameterization, lots of things. So these are used for common expected events. Exceptions, by contrast, are really best used for unexpected, rare events, but events that aren't under our control. We have to be able to handle them. These include things like, okay, so these exceptional conditions, the top ones are the ones handled by return codes and values. The bottom ones are ones that we might reasonably, in traditional languages, use exceptions for. And since the days of C, with set jump and long jump, and their sort of gnarly relatives, we've had things that are kind of like exceptions. And C++, Java, C#, pick your object-oriented language, they're going to feature exceptions quite prominently, although with different variants. So there might be exceptional conditions that we need to signify. Something like memory exhausted. That's not up to us. We can't simply say, there shall not be ever a case of memory exhausted. That's not up for us to say. That's not under our control. It's something that depends on the user's environment, etc. So we have to be able to handle it. It's a rare case. It's not a common thing. And so if we have a little bit of overhead associated with it, it's not that bad. Disk full, network unavailable, a timeout in making a connection, a broken connection or corrupt file, file not found on disk where you thought it would be, other types of data corruption. These things can happen, and we have to be able to handle them. To be mature as a software engineer, we have to be willing to handle these cases. We have no control over them. They will happen, but they'll happen infrequently. And in order to handle those, traditionally, we use exceptions. Things go wrong sometimes. So we want a way to signal that things have gone wrong and stop normal processing the code and kind of go back to a context where we've thought through how are we going to handle this error. Okay? Now, in terms of going back, what we're talking about here by go back is we go back in the call hierarchy. A calls B, B calls C, and maybe C signals the exception. The exception bubbles up. Janelle said it a few weeks ago, a few lectures ago. It bubbles up to A, right? It's a good term. Why is that? What might allow it to be handled in A that it bypasses B, or that it doesn't actually get handled by B? I should show. It actually goes along like this, but if it's handled by A, it's because what's around it? We have a try, right? We have try and catch. Think of it here, right here, right? So we have a try block, and in this try block we might call B, and B calls C, and C actually triggers an exception, so it's going to go right up to A, back from C, and it's going to go into one of these exception handlers, and hopefully it will handle it. Maybe it closes the network connection, maybe it logs something to a file, maybe it puts something in a database, and it releases some resources and waits until does a back off and waits for some time. Okay? So Java uses exceptions, Java programs use exceptions not infrequently to handle these sorts of events. And we throw the exception where it occurs, and it gets caught in handlers, and we indicate with a try statement, hey, we're setting this up so that we're going to catch certain types of exceptions, right? People familiar with this general idea? So it bubbles up until it gets handled. And the idea is someone up here hopefully has a clue about what to do. Now, that's not a tall order, because the further we get or that is a bit of a tall order, because the further we get from C, the dimmer and dimmer our understanding is of what exactly was going on down here, what the context was. But we have a more and more general sense of, okay, what are we in the middle of, and so we might stop a whole line of processing. But generally speaking, it's good practice to handle exceptions close to their source, because often you know more what resources need to be freed up, etc. So try catch blocks. Okay, so drawbacks of exceptions. We covered these in 371. We're going to see how we can do so much better with monads. Get much of the benefit of this, but do better. So drawbacks of exceptions, high performance costs. They're not free. You have to set up the bookkeeping for this. It has to remember there's a try block up here with these sorts of exceptions costs so it can bubble up and get handled. And the bubbling, it's pretty expensive to roll things back in this way. In some languages there are memory leaks, but more generally there's resource leaks. Even for in a language that's garbage collected, like Java or Scala or what have you, if we use exceptions, C#, C++, C++ is worse because there are memory leaks easily that come in there because you're doing a lot of your own memory allocation and freeing. C#, Java, languages like that, there's less likely to be memory leaks because of garbage collection, but there can still be resource leaks associated with things like files being open, databases needing to be closed, connections to other machines. And if you don't watch out, a file could be left open, it propagates up and it's never closed. Or a database connection could be left open. And that's expensive, it turns out. Opening a database connection is quite expensive. But it's also hard to recognize mistakes in code. It's hard to reason about code because we're studying some code, that's somewhere, and what's not obvious is where it can throw an exception and where it goes if an exception is thrown. We look at the code and it's just not obvious where the control flow, the next line of instruction is going to go. And it breaks abstraction rules in the sense that A calls B, and perhaps in calling B, A doesn't know anything about an exception that's going to be thrown by C. It doesn't even know that B uses C, right? The whole idea of one of the important ideas behind abstraction and modularity is that A should be able to use B based on what B does, not how it's implemented. The fact that B uses C is generally not something we want A to have to reason about. But here, A has to handle sometimes the exceptions from these things used by B. It's not very good. A has to worry about what is B using that could trigger an exception. Now, in Java, in contrast to C#, we actually have the luxury of saying, associated with a given method, what exceptions it could throw. But even there, it's not complete, because there's whole classes of exceptions, so-called runtime exceptions, that are exempt from that. You don't have to say that. And it just pushes the issue back to, well, a runtime exception might occur from C, and somehow A has to be prepared to handle it, or else the user is going to get a rude message and the program is going to die. So it kind of breaks abstraction, and it breaks the processing. In the middle of this processing, something happens like a divide by zero, and suddenly that processing line has been discontinued. Just because of one lousy divide by zero. Now you've broken the pipeline, and suddenly you're in a different place to handle this. Not very scalable, ladies and gentlemen. Not very scalable. And that's the point we're going to be, hey, look at that, I've seen that before. They remember me taking a photo of it. Okay, so here, ladies and gentlemen, the meaning of code, where it goes next, is context dependent. It depends who called us. This code, if this triggers an exception, where is it going? It depends who's called us, which is a little bit disconcerting. It has high performance cost and, in fact, lack of really rigorous type safety. You have difficulty composing it to higher order functions. Imagine now we have a function that takes a function in as an argument. And that function it takes in as an argument can throw an exception. How the heck are we going to have our function that takes this argument, like this guy here, how is it going to be able to handle exceptions from all the different functions that can be passed to us? It's bad news. That way lies madness. Okay? It's not realistic to restrict the functions according to the exception that passed into a higher order function according to the exceptions. To say, oh, map only can be used with ones that can handle these exceptions or something like this, something along those lines. And generally it's kind of difficult to reason about where the control is going to go and risk of resource linkage. Okay? And there's just cruft and bloat around us, verbosity and handling it. In 371, I talked a little bit more about this, handling as soon as possible, translating exception to meaningful languages, using checked exceptions rather than runtime exceptions, reusing common ones, documenting cause. These are good things. Exceptions are good. What does an exception give you? In terms of information for the user, how does it compare with a return code? I'm not saying you use them in the same circumstance. Return codes are used in common circumstances. But what else do you get with an exception in terms of information?
Okay. What went wrong?
Yeah, what went wrong? Where it went wrong. Right? You can get actually information on the stack trace from there. In fact, teaching 371 historically about 80 to 90% of the student code I've seen in exception handlers is just dump stack trace. Bomb out. It's like an abdication of responsibility. I'm out of here. Yeah, you deal with it. Not a very good thing to endear yourself to real world users. I will strongly discourage that. Okay. Okay, let's talk a little bit about assertions. We're going to come back to this, and I'm going to go light on it right now because I want to get us somewhere else. We're going to come back to this and see how it can be done better. But the idea of assertions, ladies and gentlemen, is we're alerting a programmer to misplaced assumptions as soon as possible. If this program has an error, it has a bug, we want to find it as soon as possible. If there's an underlying fault, we want to know about it as soon as possible. And an assertion documents assumption, checks the assumptions, and it reduces the likelihood the error will slip through testing, will slip through exploratory use of the program. And it really reduces debugging time because it means you find the error closer to its source. You find the fault closer to it because you make a failure occur closer to an underlying fault if there is a fault there. And it helps improve the thoroughness of the test. Rather than going 5 minutes before a failure comes up, you catch it after hundreds of milliseconds. You're much closer to the underlying fault, and it makes debugging easier. Do you folks appreciate that? Yeah. Look at that. Faults, failures. Okay. Okay. So faults, ladies and gentlemen, lead to failures, and an assertion means the failure will occur, more quickly, and it can allow for rapid debugging. Sorry to some of you have to. I'm adding insult to injury. I mean, the original handwriting is bad, and for you to have to read a grainy version of it is terrible. So the idea here is part of offensive programming. If there's a problem, you want to find it as soon as possible. That's a good lesson for life. If we have issues, we want to know about them soon so we can learn from them and do better next time. So the assertion goal is to fail early if there's a fault, right? And often you're checking preconditions, postconditions, invariants, and history properties. But we're going to come back and see how a language like Scala can help us do this even better. Okay. Good. Assertions in Scala are supported by 4 major constructs. Okay? We're going to see these. One is requires. This allows us to check a precondition. They actually separate requires from assert. The idea is requires is about unchecking things that someone else should have guaranteed who's called this method or called this bit of code. it's the responsibility of a client to, and I don't mean the end user, but I mean some other piece of code that's called me. And typically it's used for preconditions. I'm checking this precondition. I'm checking this thing I need, that I've stated, I need this to get my job done. Have they given me what I need to have my job done? If not, there's a problem. There's a programmer error. Assertions are all about programmer errors, developer errors. With requires, the developer might be a different developer. I'm working on this little method, and it's whoever calls me. Oh, maybe it's my code that calls this, but the actual problem is somewhere else in the code base. So I might check this to the top of a method. Have I been passed a null pointer for this? Passed a null reference? If so, it's a requirement failure. So I'd say requires this certain parameter name not be null. Does that make sense? Okay, an assertion is used to check assumptions in Scala regarding things that are largely computed under sort of the control of this module. It's not a totally crisp line between these, but it's kind of a useful distinction. Is the error probably in someone else's code or some code elsewhere, or is it in this particular method? So maybe I assert that this thing that I've been computing, I assert that the intermediate value has some property. And if there's a problem here, chances are it may well be a problem in my code. So I assert that. Okay? There's another thing called ensuring, which we'll see, where we check post conditions on things. And then there's something called assume, which basically says, hey, look, it'll be checked, but basically you can assume this from now on. So here we go. Here's a bit of Scala code. My map and append general, okay? Here we go. This is just what we created. But we might create an ensuring. Remember, this is to check a post condition. Well, what post condition is this checking? Anyone? I'll give you a hint. The underbar here is the return value. Yeah.
So looking at appending two things together and checking that the length of the
That's right.
thing is equal to Singapore.
Exactly. Is the thing being returned, is at least its length right? We could check other things. We could check, is the thing being returned, for example, is the first element of the thing being returned the same as this function applied to the first element of sequence 1? That would be a further check. The goal here is not to have 100% confidence what you've returned is correct. Generally, you can't ensure that, but you could rule out whole classes of errors. Yeah, Warren.
Can you do that lazily? Because I imagine a lot of these things wouldn't work on something like a stream.
Good question. Yeah. So it would often, if you were returning a stream, you'd probably have to look at least at the first element of the stream to check anything meaningful to it. But you could check that it's not an empty stream right away, right? So with laziness, there's some limits, but basically you could check some things. And one of the hallmarks of assertions, ladies and gentlemen, one of the hallmarks of having explicit constructs in the language for assertions, like ensuring, assume, requires, is that we could turn them on and off without stripping them out of the code base. We can actually just tell the compiler, enable these, disable these. Some people don't like the idea of users getting code which has assertions in there, and they might want to disable them. Or maybe an assertion is very expensive because it compares the result of this algorithm versus that one. And in Java, we can turn it on. And I think by Scala, by extension, you can turn them on and off on a per module basis. You say, hey, enable assertions here, disable them in that module. Okay, so this is ensuring. This is a post condition check in Scala. And you notice that it operates on the value returned by the function here, okay? So this is the value of the function. It's actually checking it. If we had curly brackets here, because we had a bunch of successive operations to perform, it would be performed in the last one, or this would appear just outside the curly brackets. Ensuring, okay? Or you might have something like this. Here, index for closest element. So here I have a sequence, and I have an index, which denotes one of the elements of this sequence. And the goal of this function is to find the index of any other element that's closest in value to the one at this index. So here I have an ensuring clause which basically checks, okay, is the one being returned, is it either 0 itself, or is it such that whatever is value, is it at index 0, or is it such that whatever value is at that index is closer to the ordained value than ones at sequence 0. This should actually be less than or equal to. So basically, it's not guaranteeing that it's not checking the thing being returned, the index being returned is, in fact, has the closest value, but it's at least checking that it's at least closer to the one that I'm trying to be close to than the first item in this sequence is. Okay, so that's an ensuring clause that just does a sanity check. But then there's a requires clause, which basically says, look, is this sequence length greater than or equal to 2, which might be something I stipulate. I want something with at least 2 elements, because I've got one specified and I want to find the other one that's closest. And, is this one that I've specified compatible with? Does it fit within the sequence? You see what I mean? It fits within the sequence. It's a valid index into the sequence. That is, its value is greater than or equal to 0, and its length it's less than the sequence length. Okay? So this is use of require and ensuring in Scala to check preconditions and check postconditions. Note here, this ensuring is applied on the entire value returned by this block. Remember, everything in Scala, like these constructs within this context, is an expression. I have semicolons. We don't need semicolons here. They're just to separate lines. I shouldn't have put them in. What we're doing here is we're getting the return value, whatever value returns from this, and we're checking this on the way out. But we're checking in a way that still allows us to enjoy recourse to naming the arguments here, sequence, for example. Okay? Do people want me to spend more time on this? Are you comfortable with this?
I have a question.
Good.
This,
Excellent.
So this ensuring, it always receives something, right?
It always receives the value that is being returned. That's correct.
So I can say that it's being applied to an expression that's returned from a
Yeah.
function. So does it work with any sort of object?
It does.
That returns anything?
Yes, it does. Yeah, that's right. And in fact, I'm 95% certain that it actually will work even if this is a procedure. Okay, in other words, even if it doesn't return a value. We talk in Scala about it. Scala avoids the horror of saying this being returned is void. It doesn't say it's a void. Void is horribly overused in the C language context. But what you would write is, if this were just a procedure, it just does something. It doesn't actually return something. You leave out the equal sign here, and there it won't actually return something, but it sure could still verify potentially some property of global state, for example. That, or some, but the surrounding environment that it's changed, that a certain network connection is now open, or what have you. Yeah,
So
Warren.
what happens if the ensuring condition is not met?
It will print a message which says bad things happen. Okay, let's try this. Where it works particularly beautiful is with frameworks like Scala Test, where actually it will show you the exact expression you're testing, and it will give you the value of the different components of it visually to sort of tell you, okay, this is what went wrong. So let's try this, right? Require, oh man, that would be bad. Computer science might cease to exist as a discipline if that were true. Oh my gosh, sorry. Okay, it would have crashed anyway. Okay, there we go. Notice it throws an exception, right? I could do assert in the same way. Assert, let's do it to this, okay? Yes, it checks it. And if this happens, it fails. Notice it's a different exception that's thrown. Assertion failed versus requirement failed. But it's going to provide information about what went wrong, okay? And I won't go into it, but ensuring would throw a similar message, okay? So it gives you some understanding of what went wrong, where did it go wrong, when did it go wrong, etc. Is that okay, Warren? Yeah, okay. Okay, oh man, I did this to 371. We don't need to do it. If any of you are interested, I have a bunch of examples of using assertions here, which basically, this is Java, so we use assert. And Java is the special syntax where we can specify a return message to be used. And I think assert in Scala may do the same. Not sure. Let's try foo. I don't. Yeah, foo. See, here's our message. So bad. And it failed, right? But if it succeeded, it won't say it. So similar idea in Java. Here it's checking things, but Java doesn't distinguish between requires, assume, assert, and ensuring. But we can do similar things in Java. So I give a bunch of examples of where assertions can be used. Assertions, ladies and gentlemen, I want to. By the way, I also show how to enable and disable assertions. Somehow the formatting got it within the Java context on a per module basis. Okay, let's talk about these three problem handling approaches that I've covered thus far. Return codes, traditionally used to cover common expected events. They don't have special language support, and therefore things can fall through the cracks. Nothing forcing you to handle this weird condition. Nothing distinguishing the -1 from a valid index. So you can end up misusing it as if it's an index. Exceptions are used for unexpected rare events. They do have special language support. They can unwrap the stack as we bubble and boil. And they do appear in debug code, but they're quite expensive. And they're confusing. They're not type safe. They break pipelines of processing. They bring you out of there rather than allowing you to sort of go forward with just a warning. And then assertions. Assertions are used for logic mistakes, developer mistakes. These things should never occur if your program is correct. But because they do occur, because we have flaws, we make mistakes, we litter our code with assertions. They're a different sort of thing, though. These ones are things we want to check for because we may have made a mistake. Return codes or exceptions are things we have to handle because the world is sometimes an ugly place, and we have to handle conditions we would prefer not to deal with, but we have to. You do not want to use an assertion, ladies and gentlemen, to simply rule out something that is not under your control. So, for example, here is a misuse of assertions. This is from Steve McGuire, an old colleague from my youth in writing solid code. Here, an assertion is incorrectly used, and he was showing it as an incorrect use of an assertion to check that the results of a memory allocation, whether or not they've succeeded. In other words, was memory available to be allocated? Why would you not do this with an assert?
You can't recover.
Yeah, you can't recover, but more than that, also, this is not, we can't simply say, we're not going to handle, as a mature developer, with code that we're shipping to people, we can't simply say, there are no cases where memory allocation fails. There will be. You're out of memory. You got to be able to handle that. That's not under our control whether or not memory can be allocated or not. We have to be able to handle it. To be a mature programmer, we have to handle case where memory is misallocated. By contrast, we can assert things which involve things that are under our control. Memory allocation, whether it fails or not, is not under our control as developers. What is under our control is correctness of our code. And so we assert things that basically do sanity checks on our understanding, our sort of assumptions about the code. That's what assertions are used for. To do sanity checks that our assumptions here are in fact grounded, that they're in fact correct. Now, beyond checking it operationally when this runs, beyond throwing something here if you can't find this when it's part of the stipulation that it's got to be present in there. This would indicate, if this is reached, it indicates a programmer mistake. But it also documents our assumptions. The fact that we have assertions in our code, it documents to readers of the code what we're assuming. It documents that we are assuming these things. And that often is really useful in terms of self-documenting code. Do people grok that? Okay, good. Okay, so a little bit of comments here. We now are going to go on and look at things that we couldn't look at within the context of 371, but which are of great significance. And that concerns how we can do this much better, okay? We're going to be talking now, ladies and gentlemen, about this last type, monads, okay? We're going to be talking about how we can use them to do one better than each of these. Okay, so let's take a look at this. So I think I am going to switch over to this presentation. Here I actually have some relevant slides in both and might switch back. So now we're going on to the issue of robust and scalable error handling using monads, okay? So just to recall, exceptions, lack of referential transparency, high performance cost, lack of type safety, difficulty of composing into higher order functions, difficulty of reasoning about them, and just to give you a sense of this, well, let's do this. Hey, let's get your fingers doing the walking. So, ladies and gentlemen, I'd like you to call up your Scala shell, if it isn't already called up. And I'd like you to do the following. So first of all, import scala.util.random. Import scala.util.random. Okay? There we go. Underbar means, hey, import everything in there. Okay? Okay, now we're going to do this vector. We're going to create vectors of size what? 10. Good. And we're going to do next double. What is this next double? Anyone remember? Yeah, and so what does it mean? Am I passing in a particular double? No, this is called by okay, that's I should have said .fill, sir. What am I doing? Sorry. Vector.fill. Glad I'm not doing a dissertation defense this morning. Vector.fill of 10, next double. So what is this thing being passed in? Is this a particular number? No. It's a recipe for how to create it. It's being passed by name. So here's a vector of size 10. We're doing next double. And I'm going to do something kind of nice on it, ladies and gentlemen. I'm going to filter it, and I'm going to look for all of those that are greater than 0.95, and I'm going to add them up. Reduce this plus this. I'm going to add up all of those that are greater than 0.95. Oh, sorry. Sorry. Okay, greater than, you know what? I'm going to do this at first with 0.5. Just, I think didactically, this is a little bit better. Ready? So what does this do? It returns a double. And that double, the meaning of the double is what? It's the sum of all numbers in here that were greater than 0.5, right? Here we go. 4.6, 2.9, 4.8. Good stuff, right? Okay, now let's change it. Let's make this greater than 0.75. Well, 0.9, okay? I'm going to make it greater than 0.85. 0.89. These are going down because there's fewer of them of that size, but the numbers are bigger actually. So, but there's fewer of them, so it outweighs the greater size. I'm gonna do a 0.95. Okay, great. And let's do it again. Oh my gosh, what happened? Wait a minute. Oh my gosh, but sometimes it works. Sometimes I get an exception failure. What's going on?
Sometimes it doesn't have.
You're trying to reduce and there's problems?
Try to reduce because sometimes what?
It's empty.
It's empty. There's nothing to reduce, ladies and gentlemen. There's nothing to reduce sometimes. Oh, look, there's nothing there. Nothing. Oh my gosh. Nothing. Here's one. I was on a lucky streak for a while. Okay. So ladies and gentlemen, this is disconcerting. Maybe it's not disconcerting for you, but it's actually troubling for me. Why is it troubling? Well, okay, it's not deterministic. That's kind of where, because we're using these pseudo-random numbers. So that's a little bit baked into the example. But what else is troubling about it? Well, the thing that troubles me is we've seen that these expressions can actually be quite long. And that doesn't mean they all have to be on the same line. I mean, I'm using that for class purposes. But often we'll have long expressions. Maybe they're in streams or other things that stretch out and different parts of it get done in different places. But the point is, conceptually, it's a pipeline. There's stages of processing. And what this is saying is basically, by the happenstance of the data, just chance data events, that pipeline could be ruptured. It could be disrupted in the middle of it. And suddenly you bomb out of it with some exception. This is a little bit disconcerting because this is, after all, just another possibility in terms of the data. And we'd like to have reduce performed in a way that's scalable, that can handle any number of data items, etc. And yet here it's bombing out in the middle. And if we get an exception, where were we within the processing? It's not immediately clear. You have to go sleuth it. So there's something kind of disconcerting to the prospects of doing this kind of pipeline incremental computation that we're talking about. There's something disconcerting about exceptions. And if I had my time and druthers, I could talk about referential transparency and how this violates it. But I'll leave that for the 340. This here, we're dealing with a situation from a software engineering standpoint. We'd like modular, composable pieces of functionality. And pipelines give us that for the most part. But then if something goes wrong, we bomb out. So let me show you something. And it may cause, ladies and gentlemen, a buzzing, blooming confusion. But out of that blooming, the seed will be planted for a beautiful flower. Okay? Maybe I should defend today. Okay, so we're going to say reduce option instead here. Okay? this is going to give us a value when it's computed that encodes this value. When it doesn't get computed, it's going to give us a value that indicates that it's no value. But don't think of this as a null. It's not a null. It's much more powerful. It's a different type. This is no longer returning, ladies and gentlemen, a double. What is it returning? A monad. It's returning what monad? Option double. This is kind of like a maybe double. I might have a double, or I might not. And it actually, we can test very easily. Do I have it or do I have it not? But more than that, ladies and gentlemen, we could do something like this. And I'll elaborate. I'm going to change this back to reduce. Imagine if after this reduce, we want to square the result. Okay? How do we square this result? We'll do it with. So we could grab it, right? We could do this val v equals this, and it died. Okay, here we go. V times v, right? Okay, there's our square of a result. Watch this though. Watch this. We're going to have it do the reduce option, and here, okay, there's a dysfunction going on here. Give me a second. There we are. Reduce option. Okay, wow, that's really odd. Okay, reduce option. And I want to do map of v goes to v times v. So now I'm adding in some extra processing. And this could be extra processing, does all sorts of things. Maybe it looks up a value in a database, and it grabs a value from there, and it does some processing on it. Maybe it runs a sophisticated algorithm. The point is, this value that's returned from the reduce, conceptually, it gets further processed by later operations, right? That's the idea. There can be a lot of operations here. Ladies and gentlemen, if I got back a none, what gets returned by that operation? None. If I got back a value, it'll actually perform the square. But if I got back a none, it actually handles the successive stages in a way to reflect that they're also getting nones, that the square of a none is a none. Yes?
Can I just say how you're rolling a 5% chance absurdly frequently?
Well,
Sorry?
He's rolling 10 times to get 5% chance. So a bit better than that, right? Yeah, that's true.
Yeah. Yeah.
Still. That's like crit success every roll.
That's getting a 29 dice. You're rolling 10 dice and one in the pot.
Yeah, so this not being over in probability stats, I won't comment on the probabilities involved in the event space, but we could analyze that, and in other classes I'd be glad to lead such discussions. Right here we have some things to cover still. Yeah.
So you're calling like map on the monad, right?
Correct.
But like if you just had a reduce without the option,
It would be actually a number of them, and that's why I did the thing up there with multiplying.
so like it would be a single value, right?
Correct.
So in that case, map wouldn't work.
Correct. Yes, that is correct in this case. Yeah, that's right. So it's a good point. It actually makes it easier for us to process it. Let's be clear. This works regardless of whether or not it's produced a value or not, and that's the beauty of it. So here we've gone from a situation where an exception gets thrown and we have to handle it, and we have a special case if an exception was thrown and a catch return something indicating no value is available, otherwise return the square of the value. Here we can actually do it as part of our pipeline, actually indicate this. Okay, so let's go on here though. This is one example of brittleness. Okay, I'd like to do another one. Here. Okay, here we are. So we've already imported this. I'd like to create val randints. Okay? And this is going to be a vector.fill. Vectors rather than arrays are the preferred kind of sequential immutable data structure within Scala. And ladies and gentlemen, I'm going to do next int modulo 10 here. Okay? Note next int gives me a next integer, and I'm just taking modulo 10, so it's between 0 and 9. Okay? People comfortable with that? Great. Great. So here's our randints. This is a set of numbers here. Let's perform some processing with them. What I want to do is I'm gonna learn you some more Scala here. Okay? Sorry. So ladies and gentlemen, in Scala, we can actually create something called a pair, or a tuple, more generally. Boy, do I wish Java had built-in tuples. For years, I've been yearning for them. And although I know people who worked at Sun and went on to be, compiler architects for the team, the compiler team, and have influenced it greatly, none of them has ever offered up a tuple. Ladies and gentlemen, let me introduce you to tuples. Foo, 3, 3.14159. This is a Scala tuple. It's denoted by parentheses. Okay? It can be heterogeneous. It can have, its first element be one type, its second element be another type, a third element be a double. That'll be a third type, right? In that sense, it's a little bit different than a vector, for example, which is going to be a vector of one type. And yes, you can make it a vector of any, but the point here is this is a tuple, and we can create pairs very easily in the same mechanism, right? Here's a pair. Now, this is going to be awesome in terms of multiple return values soon enough. We'll see that probably next Tuesday, maybe next Thursday. We could have, a comma b equals some function, and then we get back two values. No passing around pointers in Scala to return multiple things. We just return them back. But our point here is a little bit different. I want to show you something that's kind of nifty. Okay? Okay, here we go. So here we're going to have val sequence equals, we're going to do, we'll have v1, vec1. There we go. Vec1, vector 1, 2, 3, and here we'll have vector 4, 5, 6. Okay, there we go. Okay, we could append these together, and we've seen that before, right? You append them together like this. Cool, now we have a vector of all of them. But another thing we could do is to zip them together. And what does that create? Anyone want to guess? Yes. We go from two different vectors to a vector of pairs of each successive element. So the first from the first vector with the first from the second vector. Remember, we had the vectors are 1, 2, 3, 4, 5, 6. So this is going to be a sequence of pairs of 1 and 4, 2 and 5, 3 and 6. See that? Now something that's, so this is a set of pairs, and so if we want to, we could map these set of pairs like this. We could say we're going to map over this, and so each one is going to be a pair, and that pair we could, do the first or the second divided by the first, right? Pair dot, and this is how you say the first of it, or the second of it rather, and this is the first of it. Okay? So I'm saying, okay, each of these is a pair, right? 1 and 4, 2 and 5, 3 and 6. Those are successive pairs within the vector. It's a vector of pairs. You see that? And now we're mapping that, meaning that we're taking that vector of pairs, and for each of those pairs in turn, we are mapping it to something. And the thing we're mapping it to is the value of the second of the pair divided by the value of the first of the pair, right? Here we go. 4, 2, 2. Whence did those come? Well, 4 divided by 1 is the 4. 5 divided by 2 is the 2. 6 divided by 3 is that 2. You get that? Okay. Pretty cool. Pretty cool. This is how you access element of the pairs. Let me show you something else, because we're going to be using this in the example here. Those who have seen Scala before might not be aware of this trick. I'm going to create, what is this thing I just created? What is this? This is a, okay, good. It's a pair of vectors, right? And then I can say dot zipped. Watch this. Dot zipped. Okay? This is actually going to give me a tuple 2 zipped. And we're going to map this. Now this is fun. A comma B, B comma A. Same thing, but basically we're mapping. Let me know. We're mapping here. We're providing a function that takes 2 arguments and then returns back that value. These were the pairs, but they're actually being accessed. Up here we have to have a function which took a pair, and then somewhat clumsily we have to access each element. Here we're actually, over this collection map, getting something that takes each of the elements of that pair directly. So it's a bit less cruft than this, and less sticky. Okay, what's the first of the pair, second of the pair? Something like that. Okay? Okay, now, yes?
Does Scala have any notions of pattern matching?
Yes. We're going to be seeing that next week. That's going to be a significant focus. And in fact, it's going to come in pretty big when you're dealing with options and tries. Okay, so here we go. Ladies and gentlemen, we are going to take successive ratios of these things. But imagine that we have a vector, okay? Call it rand ins. There's a vector, okay? Suppose we want to take ratios, take A divided by B for successive pairs in here. How do we do that? So in other words, for successive values within this. So we want to create, for example, 7 divided by 9, and 9 divided by 1, and 1 divided by 2. We want to create a vector of those quotients as ins. Okay? How would we do that?
Zip the tail.
Yeah, great. So let's try that. Let's try it in a straightforward way. So we're going to say dot zip rand ints dot tail. What might you be worried about here? Sorry? The lengths aren't the same. But you notice it actually works, and basically it's just throwing away the extra element to the first of them, right? See that? Yeah. Okay, so that's pretty nifty, at least in my book, which you may think is a strange book, but that's okay. Okay, and what we're going to do is now we're going to do mapping them. So how are we gonna create this set of quotients for them then? What do I do? Yeah, we could do that. In fact, it would be nicer if we could say rand ints comma this. Remember, a pair of vectors can become a vector of pairs by doing this with it. And then we'll do map of A comma B, and we want it to be A divided by B. Okay? A thing of beauty. Whence did this 0 come? What gave rise to the 0? 7 divided by minus 9. Whence did the minus 9 come? Yeah, integer division, minus 9 to 1. We're doing integer division for a reason. Trust me. I know most of the times you don't. It's not what you want. In this case, we do. Okay? So here we have our results. Isn't that a thing of beauty? But is it causing problems for some of you? No one? Okay, let's try this again. How if we say rand ints 2 here, right? We're going to create the same basic expression, val rand ints 2, and we are going to, boom, here we go. Val rand ints 2. The time is a ticking. I'm well aware of that. And we do this. Boom. Here we go. And I'm going to do that same expression with rand ints 2. What's going to happen? Take a look at rand ints 2. Is there something that worries you? Oh. What went wrong? Guess what? Somewhere in our data was 0. Just because our data happened to have a lousy 0 in it, our pipeline has been broken. So we're going to do something much better than this, ladies and gentlemen. We're going to do something much better than this. We are going to, just like we did with the option before, this is what we're going to do now. And to do this, in the closing minute of class, I'm going to do this. I'm going to say try. Try it. Now it works fine. It works fine, ladies and gentlemen. What have we gotten out from this? Well, we got out a vector. But are they a vector of ints? They're a vector of tries. And each try is either a success associated with an int. That's the result of that success. Or it's a failure, indicating that some exception occurred. And here's the exception. Do you see that? Divide by 0. And now, if we want, we could go and we could square them, right? We could do map, and I should really make this smaller. There we go. Come on. Smaller yet. Oh man. Okay, come on. Okay. Okay, and we could map it. So each value is squared. Good. Oops. Not a member of try. Okay. Of course. What do I need to do? I can't square a try directly. What do I have to do to it? Here, val, watch this. Val try 1 equals try of 1, okay? Here we are. Or try 2 is try of 1 divided by 0, okay? Try 1, how can I square it? What could I do? What did I do with an option before? I mapped it. So v goes to v times v, right? Great. Let's try it with try 2. I got out of it the same report. So a squaring of a failure is a failure.
So why is it not working?
Because, well, you tell me. Why is this not working? What do I have to do? This is going to be a critical point of thinking for next time. What do I have to do? Why can't I just do this? Because this v is a what?
Try.
It's a try. So what do I need to do to it?
Map it.
Map it. And, I could even do this. Dot map. V goes to v times that, right? Success, ladies and gentlemen. Success. Do you see that? This is a try. And I'm going to square that value, just like I squared, try 2 up here. If it's a success, it will square it. If it has a value, it will square it. If it doesn't have a value, it will retain the memory of what went wrong and just say I'll pass, you know. I'll pass on that, but this is the information about what went wrong. We can build a big pipeline after this. It will be robust, and we can handle this. Now, next time we're going to see how we can handle these things through pattern matching and other components. But this provides us a way to build composable, modular pipelines that can handle errors in every way as powerfully, as robustly, and in fact even more so than with traditional exception handling, and to do so much more so than return codes, because these carry privileged information that can force us to check both conditions, okay? So next time we're going to take this and take it to show how we can build robust programs. Thank you very much, and I'll look forward to seeing you next time. Yeah, what's up?
I have a question about the underscore thing in Scala.
About the
Like, you know how you use underscores? in
yeah
Scala?
yeah.
Nothing.